I've been incredibly lucky because it's not a really gorgeous day outside. So you're feeling a little less bad about wasting an afternoon here listening to some guy ramble on about requirements. Other presentations have been people telling you about all the great things they've done and perhaps a few mistakes they've made and help you learn from their experience. Other PhD students maybe shared their research with you. I'm going to share a summary of 20 years of research that I've done for no particular reason. It's just I don't do golf. I do play bridge, but I decided this was more interesting. And I've been in this game for over 50 years. Initially, I bugged, like some of you are doing. And then I decided to get into quality and test to figure out how to get rid of those pesky things. And I did that for a couple decades, and then I spent almost 20 years looking at requirements because as a quality and test guy, I was supposed to get these magnificent requirements flowing downhill, and then my job was going to be incredibly easy. I just had to develop tests against those wonderful requirements, except I only saw wonderful requirements one time, and that was an aberration because a client of the company I was working for had been using a reservation system built specifically for them, and over a 5-year period, they decided they had nothing better to do than create a massive requirements spec of the perfect reservation system for them. Other than that, it's probably looked like a lot of requirements that you have. None of you are old enough to know the significance of this title. In 1968, a famous letter was written to the communications, the ACM, by Dijkstra, who said go-to statements are considered harmful, and he made the case for why go-to statements made programs harder to understand. I'm going to claim that what we're doing as far as models in requirements engineering, except I call up development. I don't use that engineering word. Software development. Maybe we'll get to engineering. I don't know, but they're incredibly simplistic. I discovered way late into my research. So I'm going to show you why I think so. I hope all of you will kind of skeptically consider what I have to say. I don't think all of it's wrong, but possibly some of it's wrong, except I'm unable to spot the bugs in what's going on here. So my hope is that I will help you, give you a few useful things that you can take back and do possibly a better job in your workplace, and perhaps even share some of the things that you think might even be interesting in your workplace. All of these slides are available online, downloadable, so you don't have to do them again, right? What would be the purpose of that? We call reuse. Okay, so let's look. We have 4 sessions here, 5 minutes between sessions. We're going to talk about complexity, because if you don't understand what I'm talking about, that won't be very good. So we need to understand what simplistic actually means. The second one is going to go from 105, and the third one, these 2 guys are shorter, so it's the longer stuff up front when hopefully you have a few ergs of energy now and things will fade during the afternoon. Okay, understanding complexity. Well, the word complex, right, we know what that means. We know what simple means. But what does simplistic mean, you might ask? Well,
the Australian jewel beetle is dimpled, glossy, and brown. The female is flightless. The male flies, looking, of course, for a hot female. When he finds one, he alights and mates. There's another species in the outback, Homo sapiens. The male of this species has a massive brain that he uses to hunt for cold beer. And when he finds one, he drains it and sometimes throws the bottle into the outback. Now, as it happens, these bottles are dimpled, glossy, and just the right shade of brown to tickle the fancy of these beetles. The males swarm all over the bottles, trying to mate. They lose all interest in the real females. Classic case of the male leaving the female for the bottle. The species almost went extinct. Australia had to change its bottles to save its beetles. Now, the males had successfully found females for thousands, perhaps millions of years. It looked like they saw reality as it is, but apparently not. Evolution had given them a hack. A female is anything dimpled, glossy, and brown. The bigger the better. Even when crawling all over the bottle, the male couldn't discover his mistake.
He had a hack, right? He had a model of the female. A little to do with the actual females, and then the model failed big time. I mean, that's a true story. Okay, so simplistic means, right, that it's too simple, that it's not helpful. And simplistic sells. Some of you, excuse me, I'm about to throw a stone on maybe one of your favorite topics, agile. Agile, this, that, and the other thing, is beautiful as long as you ignore the details, as long as you ignore complexity. Now, this is about the 150th anniversary of one of the most successful models out there, the periodic table. Now, there is an incredibly useful model. It helped people identify where there were holes and said, maybe there's actually something there. And they went off and, my goodness, they found something they didn't know existed. So the model really helped them big time, right? For 150 years. That's super, super valuable stuff. We, you and I, all have oversimplification bias. We prefer simple solutions. We prefer unconditional statements, right? Politics is filled with this. If we only did A, B, and C, the world would be a wonderful place and this problem would be gone. Yeah, we hear a lot of that these days. There are a couple of things going on. One is our preference for simplistic models, and two is our infinite ability to deny reality. We say, oh, that piece of evidence, I'm going to ignore it. I'm going to filter it out, or I'm going to So here we have, something's just not right. Our air is clean, our water is pure, we get plenty of exercise, everything we eat is organic and free range, and nobody lives past 30. Maybe there's a few other factors there that are important. Okay, we often oversimplify. The easiest model is once upon a time there was the flat earth. Actually, there are people today that believe there's the flat earth. I don't know what percent of the population that is, but it's there. Then we had a round earth at the center of the universe, and everything revolved around us. Yeah, no egotism there. Then somebody said, wait a minute, let's try a new model where we got the sun at the center, and we got all these other things out there that we've named going around. But the problem here, see if I can go back one. Yeah, the problem here was if you were predicting the next eclipse, your math was really ugly. It was filled with all kinds of hacks. You had a factor, somebody said, what's that about? Well, I can't quite get that calculation correct with this model that the Earth is circling the sun. And then a guy named Kepler came along and said, how about ellipses? Ooh, that made it a lot easier, right? So we progressively got to something close. Is it a pure ellipse, a pure mathematical ellipse? Probably not. So there's probably still a few hacks in the calculation of the next eclipse. All right, for every complex problem, there's an answer that is clear, simple, and wrong. Because simplicity sells. Clarity sells. We love all that. Ideas should be made as simple as possible, but no simpler. We got that little phrase at the end there. That's really important. Okay, now I included this only so you can download it from the website. This is a beautiful thing about, this is the research in the upper right-hand corner, and then as we go around the loop here, things get simpler and simpler and simpler and simpler. I found that just the other day. Reality is much more complex than many imagine or want to believe, and you all know what Occam's razor is, but sometimes Occam is wrong. Sometimes there is actually somebody out there trying to get me. Not often, but requirements development is much more complex than many imagine. And how do I know that? Because I'm going to show you 3 simplistic models that are at the heart of requirements development. And there are 90,000 people that have been certified by 4 different organizations based on these 3 simplistic models. So they're running around proudly showing off their certificates. Okay. Now, what is a model, right? It represents some aspect or set of aspects of something we care about. And it's easier to think about, analyze models than it is the thing itself. So H2O, that symbol itself, is a model. And if we want to show the relationship of the oxygen to the hydrogen, we get even more information. We get the 2 H's and the O and their relationships. A simplistic model omits important aspects of what it is we're trying to focus on. There is an international standard. That's what ISO, International Standards Organization, right? You go, wow, this all over the world, really smart people came together and they created a model of quality attributes. Maybe none of you have ever seen it. It's okay, because it's simplistic. And I'll show you why. And functional, where did non-functional requirements? I love you. I love that phrase. That's like, let's study human beings. We're going to have men and non-men. That isn't going to get you really far. So we've got, these are examples of the simplicity that I'm talking about. Okay, so once upon a time I decided to draw a line and put simple on one end and complex on the other. That was my first mistake. That was too simplistic. It worked really well for simple because we had triangles and E equal MC squared, and I'm not claiming that that's necessarily simple, but as an equation we understand it. And we even understand the benzene ring because it's got a pattern that we grasp. Once we see the pattern, yes, I can remember that. It fits in our brain, right? Small, simple things fit in our brain. But what happened when I tried to go on the right side and do complexity, it split into 3 kinds. The first kind was called Essential Complexity in a paper by Brooks. And he talked about essential complexity, meaning everything that's in the model needs to be there, and there's nothing extra in the model, right? So necessary and sufficient, that old kind of stuff from mathematics. So we got the London Underground, and we've got DNA and general relativity, okay, as examples of essentially complex models of the thing we're talking about. Now, we've got some unnecessary complexity. Spaghetti code would be an example. The U.S. tax code with 4 million words in it. Let's see, it's tax season, let's start reading. Okay, I hope not. We need software actually to find our way through there. Okay, so you understand, we got necessary and sufficient. We got sufficient, but some of the stuff is unnecessary, and guess what the number 3 is, right? Yes, it is. So here we're going to move now into the notion of the models in requirements. So how about the different types of requirements? Well, we got functional and non-functional. Well, that's pretty simple and useless. There's a model you'll be seeing in a couple of minutes that is a requirements model. It's got 19 different types of requirements. They're not all on your project, but they help you think. And you go, any of this, is this relevant to anything I'm doing? Oh, it is, yeah. I would have overlooked it if I hadn't thought like that. Okay, now we have insufficient complexity, right? Or simplistic complexity. You've probably not heard that phrase before. Simplistic and complexity, what are those two words doing together? It means whatever you try to model, you haven't gotten there yet, right? You haven't gotten to essential complexity yet. So we have the Zwieback model, which is the functional and non-functional guys. They're all over. I don't want to beat on the Zwieback. I mean, software engineering body of knowledge. We got lots of different places in which these simplistic models show up. The best-selling book on requirements engineering has 4 types, okay, as opposed to the 19 you're going to see. Okay, so how about quality models? That's that ISO standard I mentioned a moment ago. The particular quality model I'm going to drag you through at the beginning in the next session has over 30 characteristics for each quality. Okay? The ISO standard has 1, the name. Okay? Well, that's good. I mean, it's like a list, and you can go, is this relevant? Not. If it is, you're done. The model isn't going to help you anymore except by identifying things that might be relevant to you. So here we have, in my estimation, insufficient complexity to get the job done, and I will argue what that's about. Okay, the software development process itself. Zwieback says there are 4 activities. Right? We've got to go out and elicit requirements, and it gives you, I don't know, several ways to do that, and then there are 3 other things, and we're going to show you a different model of what you need to do to when you're doing requirements development, what you and your teams need to do, and it's more complicated than that. Okay, so requirements development is, in my view, full of, these are 3 basic activities in software engineering, and if we haven't got them modeled anywhere near the level of complexity they actually are. Now, let's talk about risk. I don't know whether you folks hear a lot about risk on your job, but DeMarco and Lister think that risk management is project management for adults. That means if your projects are being managed properly, somebody's saying, what could go wrong? They're taking people out for beers and whatever it is to find people who have experience, who have scar tissue. What's this from? Oh, let me tell you about that scar. And then they tell you things. You go, oh, I didn't even know that could happen. Not only can happen, but it's likely to be very bad. So let me see what I can do about it to avoid it happening at all, or to mitigate, right, to reduce the pain involved if it actually does happen. That's all called mitigation, right? So we got hazards and mitigation. And it's really important that we know these things. So one of the many risk management tactics is if you got stuff out there that's too complex, you got to simplify it. So that would mean doing something like taking excessively complex code and refactoring it. Where did that word come from? I mean, factor is a perfectly nice word in mathematics. Refactor. That means it was factored once, maybe. Some code I've seen was never factored. It was just ugly and virtually unreadable. And when necessary, you've actually got to complexify. Where'd that word come from, right? That doesn't roll off your lips. You've never heard that before. Complexify. I need to make some of the models that I'm using in my job more complex than the simplistic ones that were given to me. Simplistic models limit your understanding. You may overcome them. Somebody might say, hey, we're interested in safety. Safety is important. And somebody else might raise their hand and go, what about security? Oh, are they related? Why, yes. Security supports safety. If you're doing safety, you got to be doing security. How do I know that? Not from most of the models that are out there. It was a great discovery. Well, no. How about if you have a somewhat accurate model of the relationship between qualities, then when you realize you get the ones that are really fragile and hard to achieve, one of the reasons they're fragile is because there's a bunch of others that are supporting them. And you got to pay a lot of attention to that too. You can't manage what you don't understand. Okay, so now some of you have seen this 2x2 before, right? What you know, your birthday, right? What you know you don't know, my birthday. What you know, what you don't know you know. The number of red stripes on the U.S. flag is not a number that just kind of pops into your head, but most of you can figure it out, right? And the last one is blank. There's a ton of stuff, a universe of stuff that we don't know. Now, why am I doing this? Okay, let's look at what we know. Well, some of the stuff you know ain't so. Right? Oh my goodness, we're wrong? That isn't the way the world works? It isn't the way that person thinks? Yes, it isn't. And the other thing is, the other things that we think we know are simplistic models of certain areas. And we're okay with that, because simple sells. Now, how about the lower right-hand quadrant, right? What we don't know is the truth of the stuff we've got wrong. It is the essential complexity of the thing that we've got simplistic, and a whole bunch of other stuff, okay? Why am I showing you this? Because my job is to follow this arrow, is to push up into your brains and help you understand that there's a bunch of stuff you don't know, okay? That you didn't know before you came in here. Right? And your job is to follow that arrow, okay? And to get it over there, figure out, what in the world was this screwball talking about? Maybe I should hunt around and find out. Okay, so that's the goal. So now you understand hopefully what I mean by simplistic model. Okay, so let's talk about requirements related information. I mean, there are requirements, but there's a ton of other stuff that you have to kind of gather together if it's not already in your head. Now, sometimes, if you're doing an air traffic control system for the 14th time, you got a lot of knowledge in your head. Or if you're doing billboard websites for the 14th time, the requirements are already in your head. So you don't need a lot of external support, a lot of stuff written down, because you're an expert in that particular area. There may be some new things that you can focus on, but in general, you got a lot of information that's important. Okay, so what am I talking about in this requirements-related information? Well, first of all, you got to know the application domain. So if you're doing an airline reservation system, there are certain things you want to know, flights and whatever. If you're doing an aircraft maintenance system, right, I'm kind of in the same domain of aircraft, but now it's a whole different set of things I have to worry about, right? So you not only need to understand the domain you're working in, and some of you are experts in that already, and others don't. And so we have this terrible word, ontology. Blech, Unfortunately, that's the word that people use for all the concepts that are in a particular domain. And I'm going to show you an ontology here in the next slide. The other things you need to understand as clearly as you can is the problem or opportunity that you're about to work on. You need to know who the stakeholders are, and there generally is a larger population of them than you know. The solution context, because you're developing it in the context generally of other systems and other solutions for other problems. And so your solution or opportunity needs to fit in. Right? The risks of whatever it is you're doing, the assumptions that you're making, the available restrictions on feasible solutions, i.e. the requirements, and then the requirements, risks, and mitigations. A lot of stuff to know in order that you don't get surprised. I mean, you can only know some of this, and you can lay a lot of code down and wind up with 1,000,000 lines, and then somebody goes, I'm sorry to announce that we missed this whole area that we have to produce some stuff for before we ship. Okay? That is not a message that anybody wants to carry, because you know what happens to messengers of bad news. All right, so here's an example from one of my interest areas, which is autonomous vehicles. I'm interested in this because I have 5 beautiful grandchildren who don't need to be in an autonomous vehicle. They just need to be on the roadway with an autonomous vehicle. And if those puppies aren't behaving properly, they're at risk. So as a grandfather, I'm very interested. Here, you all understand those. Look at the sets of things that need to be understood in the domain you're working in, right? So you got entities, hazards, procedures, rules, yada, yada, yada. A lot of stuff. Let's see. The requirements for autonomous vehicles. We've got a dozen or more companies around the world, all basically working the same problem. How many of you have ever seen the requirements for the systems that they are so proudly showing on LinkedIn? No hands. Well, there's a big shock, right? Okay. Now, they're all private companies, you say. They're very concerned about intellectual property. Is the requirements for self-driving vehicles intellectual property? Well, a company thinks that way, says, oh, maybe my competitor will not figure this out, and they'll kill a bunch of people. Is that going to be good for me? I don't think so. So it's like the entire industry should be really, really interested in coming up with a core set. Now, if you're doing an automated bus and somebody's doing an automated golf cart, whatever it is, yeah, there are going to be differences. But at the core, if they're on public thoroughfares, right, they basically are solving the same problem. So naively, I think there should be, open source requirements. What a concept. All right, anyway, moving right along. Okay, so we said there are functional and non-functional, or we have 19 different kinds of requirements. Okay? And I want you to notice, now not all the types are going to be relevant, right? So if you don't have a supplier, then you don't have to worry about basically the requirements for the suppliers you don't have. And I also want you to notice how often the word developers show up here. Okay? Yes, of course, basically every book or paper I've ever seen says, oh, we got to get the customer involved. Customer involvement is really key. And without question it is, folks. But that's just the beginning of the story. Developers have an enormous responsibility in a lot of areas that I think most of them don't understand. They don't understand their responsibility, and if they said, yes, that's my responsibility, they don't understand what they need to do. So that is something that an essentially complex model can do for you. It can show you whose responsibility is what and the things that you need to understand in order to do an adequate job, right? Okay, now, whenever you automate any area that has previously not been automated, it becomes really, really important to manage the terminology. Because everybody has their own private terminology. And so in an organization, when two people communicate and they see a phrase and the one person who wrote it meant this and the person who's interpreting it meant something slightly different, and sometimes those underlaps don't matter, and sometimes they're deadly. So we need glossaries. Another topic that's kind of boring until you get it wrong, right? Now we know the Tower of Babel actually is an example of something that's not too dangerous. Why? Because when the person next to me isn't talking a language I understand I don't understand. But this guy is much more dangerous, right? This is the famous Tower of Unrecognized Ambiguity. So now the person next to me says something, and I go, I got it. No, you don't. But you think you do. So for new domains or applications, terminology management is very important. Okay. Precise definitions are a pain in the neck, and they're completely inhuman. We do not go around precisely defining the terms that we use. My wife sends me to the store for orange juice. I get to the store, and I thank somebody that cell phones were invented. Because now there are 374, it's not like the cereal aisle, but it's almost as bad. There are many, many different kinds of orange juice. So I need a little refinement of my mission here, okay? That's normal, folks. That's how we operate, and I'm not proposing that we suddenly, move to Vulcan and get ultra precise about everything we say. That isn't going to happen. So the value of a precise definition is directly related to the difficulty in creating it. If everybody shares a common definition of a term, and I go, what does this term mean? And 2 minutes later, we got it written down. Not very valuable. But on the other extreme, if it was really hard to get consensus on a term, what I've done is avoided a lot of problems in the future now that we understand that we don't understand, and we don't have a common understanding. And we've got to come to one so that we can then, when we receive our marching orders to do something, I understand what the words in the marching orders mean. Okay, so now, is this creature near the roadway or not? Why do I care? Anybody want to tell me why I care? I'm sorry? He could jump in, yes, yes. Volvo did their automatic vehicle experimentation in Australia. They had algorithms for sensing animals, non-humans, that were moving in the roadway and what to do with it. But they had never encountered a kangaroo before. So when it went airborne at the driver, they weren't prepared for that. And as a matter of fact, they announced a 4-year slippage in the delivery of their self-driving car. I don't know whether they made that or not, but I thought it was just so wonderful that they recognized that there were a lot of things out there that they hadn't counted on. Whether this is near the roadway or not depends on the jumping range of that particular creature. If it's bigger and has a bigger range, the very definition of near changes, because we're talking about risk here, right? All right, requirements development. A solution requirement. Now, people talk about user requirements, where there you've labeled the requirement by its source. We're talking here, everything I'm talking about this afternoon is solution requirements, right? So a solution requirement is a restriction that determines whether some solution you come up with is adequate or not, right? So are you conformant with the HIPAA requirements on privacy, right? So are your data sets such that I cannot determine which of my customers, which of my patients have which diseases? They got to be separate and non-resolvable. If both of those data sets were somehow stolen, it should not be possible for the stealer to make an association. That's a HIPAA requirement. Okay? So you can have the most beautiful system, everything's working, except that's not true. Okay? You want to know all the restrictions, right? A proposed solution may comply with all the requirements you know about, but still be inadequate because the things that you know about aren't complete. There are important things that you know. So you never stop learning. And when you get into new domains, space station, nobody's got experience in that domain. Nobody's got experience in autonomous vehicles. I mean, there have been people who have worked in this for a decade or more. But they are still discovering a lot of interesting things. They're coming to appreciate how incredibly powerful you and I are, our little human brains. And now my 18-year-old or 19-year-old, their brain isn't fully formed yet. I'm really worried about them on the road, but anyway. Okay. So some believe that poor requirements are a leading cause of project failures. That's why any of this stuff this afternoon is important, right? Some people don't believe that. Poor requirements cause this stuff. 54% of the requirements faults on space station were things that people didn't get. Well, big surprise. You would expect most of the things to be there because nobody had any experience. And so all they could do was imagine. That's why Albert Einstein talked about that imagination is much more important the knowledge, right? If you want to get to the next level of something, do something that's never been done before, you got to imagine. You got to have a wonderful imagination. And you have people who say, no, that'll never happen. Right. Only it'll wait for the second day that the system is in place. Good requirements matter. Simplistic models don't help. Okay, the goal of requirements development. What I would like to do, without the Vulcan mind meld, okay, is I want my team to have a deep, synchronized, and accurate understanding of what we need to do, what needs to be done, right? Synchronized. That means everybody's in the community has got a similar image. Oh, look at that. How wonderful it is. Well, wait a minute. Why are penguins imagining tire swings? Well, some of you may or may not understand that, but it doesn't matter. Okay, this is what I want. This is rare. This image with human beings there are even rarer, that everybody is literally on the same page. We use that phrase so easily, but it's incredibly hard to get it because we all have a lot of stuff going on inside our head that causes that not to be true. Okay, so here, the third model was the basic pattern of actual software requirements development itself. So the first thing, the simplistic model says elicit. This model says acquire, because there are about 20 different ways to acquire information about what we want to do. When I came back from teaching overseas, I went to work for a company. They handed me a listing, and I said, yes, what am I supposed to do with this? They said, understand it. So I was much more naive then than I am now. I said, okay, I sharpened up my 3 number 2 pencils, and I took out my template, flowchart. I think I was just going to flowchart my way into understanding. Well, that didn't work. This particular listing had a go-to density that has never been surpassed. It also used completely meaningless labels for everything. For the sections, for the data, nothing. And so after I told my manager I'd have it done in a week, and I went back after 3 days and said, I think we're going to have to adjust that. I have no idea what I'm going to get done. And I started having to move lines of code around, having no idea what they did, but there was a go-to here, and it jumped up here, and then it jumped back there, and I thought, wait, why can't I just move this and get rid of those go-tos? And sometimes it worked, and sometimes it didn't. And it's only until I began to straighten out some of the strands of spaghetti that I began to think I understood maybe what this code was doing. 3 months later, I went to my manager and I said, I understand it. He said, good, and your prize is to rewrite it. Right? So that's one way, a very painful way of figuring out what the requirements are by reverse engineering, in this case, an incredibly opaque set of code. That's just one of 20 different things to do. Yes, asking the users is incredibly important, but that's just one of those 20. Then you got to analyze what you got, because sometimes we have conflicts. Many of you are aware of security and usability. Now, maybe you enjoy answering the 3 security questions that you could barely remember what you claimed the answers were. I don't, and I don't find it increases the usability. But I know I have to get through this wall that they've built in order to get to, hopefully, a much more usable piece of software on the other side. And sometimes there are derivations. if I discover that I have to do safety, from that responsibility becomes hazard analysis. I got to figure out all of the things that can go wrong. I once worked for a company in town as a consultant, and I was mightily impressed because the first thing they did was have a senior engineer write down all the ways that the device they were concerned about could kill people. And it was a very long list. And I went, wow, that's an interesting way to start the project, okay? Then they had to say, well, this can't happen because of this can't happen because of this. This can happen, but we can mitigate that by doing this. And so all the mitigations line up against all the hazards. All the hazards? Did we forget maybe one or two? How do we know that we got them all? Well, we ask a lot of smart people to review the hazard list. We make it as public as possible to let as many people as appropriate look it over, and then we're still worried. And we keep our eyes peeled for something that none of us ever expected was even possible. Okay, now these things are all optional. That's what the square brackets mean. Why are they optional? Because if you're doing your, nth reservation system or your nth billboard website, you have a lot of internal knowledge about what you need to know. So you want to know whether your customer likes light green or tan. Why? Because you've learned over time that those are very good background colors, and you want to know what this particular customer wants. So you are driving a lot of answers. The customer doesn't even know why necessarily you're asking. You know much more. They just came to you and said, I need a billboard. All right. They didn't even use the word, I need a website for my business. And immediately you have this big long list of questions that you need to ask them. But not what the requirements are for that. You know that. So that's why all these guys, notice the middle guy there, designing system architecture. Some of the people at the SEI, Software Engineering Institute, feel that knowledge of the quality attribute requirements is very important in selecting the architecture. Okay? Now again, we gotta give and take there, right? The architect might say, okay, these are 3 or 4 possible architectures. Let me see what information I can gather about the quality attributes. This is like security, performance, yada, yada, yada. There are over 60 of them. And then I'm going to winnow it down to 1. And then once you've got that one architecture, then you have 3 jobs. 3 strategies you need to develop. 1 for each of the quality attributes that you've identified for your system. How are you going to achieve it? How are you going to verify it? And how are you going to monitor it? We're in the age of complexity, folks, and think that you all know this, and it's not getting any simpler. So we actually have to monitor stuff after we think we've done everything that needed to be done, right? We claim we achieved it, we claim we verified it, and then we have unanticipated acceleration. What? We're back in the automated vehicles again, but we're just starting. I did a little research and discovered that unanticipated acceleration has been around since 1940. Now, there wasn't much software inside the cars there, but for some reason, they would accelerate without anybody putting their foot on the accelerator. And now we've got software-based stuff. And now somebody in Florida is tearing down a freeway at 2 in the morning, and his BMW is accelerating 80, 85, 90, 95. Now he's got, something akin to Forgot the name of the system that GM has, but whatever, they're talking to somebody, right? And somebody says, have you turned the motor off? Have you turned the key? Yes. OnStar, thank you. So it's not OnStar, but it's akin to that, whatever the BMW folks call it. Anyway, so he's talking. The person on the other end of the line is talking and asking if he's done all these things. He said, I put it into neutral, I've turned it off, and it's still accelerating. And they notified the police, and the police put down these tire scramblers on the road, and for reasons I have never understood, he drove around the first one, or the car did. I don't know, maybe he wasn't in control. Then they put some more down a quarter mile further, and it went over that, and a quarter mile later, it stopped and started to smoke. And he got out. Now, after kind of a harrowing experience like that, how would you feel when the representatives of BMW said, oh, that can't happen? We've got very smart software engineers who have put code in there to check what's going on. So it's not possible. You must have not done one of those things that you claimed you did. Ooh, I would just kind of run out to my BMW dealer and get a new one. If you take nothing else away from this afternoon, folks, here's the bottom line. You've got to respect complexity, which means that the systems you're building may do things that you have no idea how in the world. I mean, it wasn't, I did a function and it did something else. I'm talking about some really serious misbehavior on the part of the software for reasons you don't understand. The Therac 25, a device out of Canada, killed 4 people before they discovered what was going on. And they only discovered what was going on because it killed 2 people at one hospital. And what they found was that when an operator of this device set it in motion and realized that it had been set in the wrong mode, which was in the manual, what you're supposed to do when that happens, and they did it. But when they did it the first year the device was there, everything worked great. When they did it the second year, those operators had become very familiar with the device. And so they were able to type the switchover commands much more quickly. Their typing speed caused a buffer overflow and set the device into a death state. Who's going to figure that out beforehand? Right? So you need software in there that says, excuse me, you can't get into the death state. I don't care what else is going on in the device. When it comes down to here, and you're going to slide the lead shielding off of the radiation source, which is set to high, you're not going to do it. Right? A whole separate monitor, separate from anything else that's there. You can't imagine how that code will ever execute. Of course, you got to make it execute and test to make sure it actually works. But it doesn't matter whether you can imagine how. In the face of complexity, you go, I'm sure there's a way. Let me make sure we don't kill anybody. Okay, how do we acquire this information? I already talked about reverse engineering. We can watch something, do association, derivation, and generalization on what we've got, et cetera, et cetera, et cetera. Nice long list. Only half the list, we analyze all this other stuff. There are lots of ways to get information, requirements-related information. Now, not all of these are going to be relevant to you. Okay? This is my favorite book in requirements. And there is a copy in the library. Whatever this little library in the office of the master's program, there is, I am positive, a copy on the shelf. Well, maybe I'm not positive. I put one there last week. I don't know, maybe somebody's borrowed it. But anyway, of these 20, it maybe catches 12 or 13, but is the best by far of anything that's out there. Okay. Now, the bad news is, when you're doing really complex systems and you've never done it before, guess what? Requirements is a never-ending story, right? You're going to discover stuff. You need to have a system set up to capture the stuff. Yes, there will be the first weeks, the first months, whatever, but then in the second year, remember the THERAC 25, something might happen that has never happened before, and you need to be on top of it. React quickly, figure out what it was, figure out what changes there need to be made to the system, yada, yada, yada. Okay, so let's take a break for 5 minutes. I'm happy to answer questions at any time. I will be staying afterwards if any of you are gluttons for punishment.